Great.
All right.
It's a great pleasure to announce today's speaker, who is Bjoern Bringmann, who is at the Institute for Advanced Study in Princeton University. He's a rising star in the field of nonlinear PDE and stochastic analysis. He obtained his PhD only last year under the supervision of Terence Tao, and he's in particular known for his works on nonlinear dispersive equations, such as nonlinear wave and Schrödinger equations with connections to Euclidean field theory, which I think we'll hear about today. Thank you.
Okay, yeah, thank you very much for the way too kind introduction, and also thank you all for coming. Yeah, so as was already kind of alluded to, I'll speak a little bit about invariant Gibbs measures for the three-dimensional cubic nonlinear wave equation. So let's take a quick look at what we've planned for today. So because this is kind of a mixed audience, I'll actually start with about 10 minutes on Hamiltonian ODEs and Langevin equations. Okay, so this will be a rather kind of slow-paced introduction, and it allows me to introduce some of the concepts in kind of a simpler setting, right? And then I'll eventually get to kind of the background and our main result. And in the remainder of this talk, I'll then try to give you an overview of the proof. Okay. At the very end, if I have time, I'll give you a little bit of an outlook on the geometric setting, but I might not have time for this. Let's see how it goes. Okay. So let's start with an introduction. So if during these first 10 minutes you want to have a physical system in mind, you can, and it would be this harmonic oscillator or this oscillator here. So I took a ball, attached it to a spring, and then distorted it away from its equilibrium, right? So this will start oscillating. And there are two variables that I need to keep track of. One is the position, which is Q, and the other one is the momentum, which is P, right? Now, when I try to model the system, there's essentially one choice that I get to make, which is the potential energy, okay? And for this introduction, I'll choose the potential energy to be of this form here. So it will have one quadratic term, which is Q squared, and potentially one quadratic term, which is this Q to the 4 here, right? So this comes with a prefactor, lambda, which is a fixed number, right? And this will always be non-negative, which implies that this is a nice non-negative quantity, okay? But I am allowing this to be 0, okay? So if it's 0, I just get the quadratic term. If it's positive, then I also have the quadratic term, okay? Now, once I have the potential energy, I can define the Hamiltonian, which corresponds to the total energy of the system. And this is now a function of both the position and of the momentum. And it consists of the potential energy plus the kinetic term. So plus the quadratic term in P. Okay, this will be our Hamiltonian. Now, if you like Hamiltonian mechanics, you can write on a first order system, and it will look like this. Okay, so this kind of system here is described by this first order system right here. So the first derivative of Q is given by the P derivative of H, and the first derivative of P is given by minus the Q derivative of H. Okay. Now, if you're more a fan of Newtonian mechanics, you would actually maybe prefer a second order viewpoint on this. So you can also write this as a second order equation for Q. And here on the left-hand side, you would have the second derivative, which is the acceleration. And on the right-hand side, you would have the force, which is minus Q minus lambda times Q to the 3. Okay. Now, another main player in kind of the title of this talk and in the rest of this talk is the so-called Gibbs measure. So let's talk about this Gibbs measure in the setting of Hamiltonian ODEs. Okay, so this Gibbs measure is defined as follows. It will be a measure on R2, so it will be a measure of Q and P, and it consists of 3 separate parts. Okay, so I have this Z minus here, which is a normalization constant. So this will just turn this into a probability measure. Then I have this exponential factor that contains the negative of the Hamiltonian, and then I have the Lebesgue measures in both Q and P, right? And at least for the energies that we were interested in, it's clear that this is a nice, well-defined probability measure. Okay. Now, to be a little bit more specific, we made this assumption of our potential energy, and I can insert this into my definition. And what I get out is the expression right here. Okay, so the only thing that I did that didn't appear on the line above is that I separated the exponential of the quadratic terms from the exponential with the quadratic term. Okay. Now, if this prefactor lambda that we had here is 0, then this term here will just be constant, right? It will just be 1. And in that case, I will actually see a Gaussian measure, which is a very good friend from probability theory, right? Now, if lambda is positive, then this argument here will be non-positive. And as a result, this exponential will be bounded by 1. Okay, so even though if lambda is positive, this measure will no longer be Gaussian, it will still be absolutely continuous with respect to the Gaussian measure. And it's a very strong form of absolute continuity, right? The density is not just L1, it's bounded, it's differentiable, it's everything you could hope for, right? Just kind of a teaser to a little bit later. So this type of absolute continuity can actually fail in the PDE setting. Okay, so this is something that we'll encounter a little bit later. Now, why do we care about this Gibbs measure in connection with the Hamiltonian ODE? So we care about it because of the following theorem, which are just called invariants. Okay, so this theorem tells you that this Gibbs measure mu is invariant under the Hamiltonian flow. Okay, so I know that not everybody here works with invariant measures, so let me just put this into slightly different words that some of you may find a little bit more helpful. Okay, so let's assume that I have my initial data, Q0 and P0, and let's assume that this is not just a fixed vector, it's a random vector, right? And this random vector is supposed to have the law given by the Gibbs measure. Okay, that makes sense because the Gibbs measure is a probability measure, right? And then this theorem tells you that the law of Qt and Pt, so the solution at some later time, is still given by this Gibbs measure for every time t. Okay, so this law does not change in time. It always corresponds to the Gibbs measure, and this is why we call it invariance, right? Now, the theorem is actually not too hard to prove. You can find it in many ODE textbooks, and it essentially relies on two different ingredients. Okay, so first of all, one ingredient would be conservation of energy. And this will tell you that this Hamiltonian here is actually constant along the orbits of the flow. And the second ingredient would be Liouville's theorem for divergence-free vector fields. Okay, turns out that every Hamiltonian vector field is always divergence-free. And as a result, the corresponding flow preserves the Lebesgue measure, which is here. Okay, and then you put these two things together and you arrive at our theorem, right? So that's roughly how it's proven. Okay. Now, there's a slightly different setting which has a similar result, and we'll also need that different setting a little bit later in this talk. So let me already introduce it here. So this setting concerns Langevin equations, or as I was recently told, more precisely overdamped Langevin equations. Okay, so this is no longer an ordinary differential equation, but it's a stochastic differential equation. We see this here in this top left corner. So the E to differential of Q is given by minus V prime Q dt. So this is a drift term plus a stochastic forcing, which comes in the form of square root of 2 times the derivative of a Brownian motion, right? And for those of you that don't work with SDEs very often, here's also a picture of what a solution to this may look like. Okay, so locally, it looks very much like Brownian motion, but then the global behavior is a bit different because we have this additional drift term right here. Okay. Now, in the setting, as I promised, there's a very similar result that I also just call theorem invariance. Okay, and it tells you that this measure nu that I defined here is invariant under the Langevin dynamics. Okay, so this measure looks very, very similar to what we had before. We have a normalization constant, we have an exponential factor, and we have a Lebesgue measure in Q. Right, so it's now a measure on R instead of R2, but it looks very similar to what we had before. Okay. Now, the proof of this is a tiny bit more complicated maybe than the previous one, but not so much. Essentially, it just boils down to Ito's formula, right? So that's the main ingredient that you would need here. Okay. Now, I do want to make kind of one remark or emphasize something, which will be important for us later. So we now have these two different measures. We have this Gibbs measure that I defined on the last slide, and we have this measure nu that I defined here. And technically speaking, they're not the same measure because one of them is defined on R and the other one is defined on R2. But morally speaking, you should really view them as being the same measure. Okay. The reason is that you can write this Gibbs measure that I denoted by mu as a product of this measure nu viewed as a measure on Q and a Gaussian measure in P, right? And because taking products is easy and Gaussians are easy, you should really view them as being roughly the same. Okay. Now, let me end this introduction by just making a quick summary. So what we saw is that once we've chosen our potential energy, so this was the one choice that we got to make, we can define a Gibbs measure, we can define a Langevin equation, and we can define a Hamiltonian equation, right? So all of these three different objects are linked via the potential energy. So let me continue to actual kind of PDEs, but this might be a good time to quickly stop and see if anybody has a question. Okay. Okay, so but feel free to interrupt me whenever something comes up. Okay, so let's actually talk a little bit about the PDE framework. So what we now want to do is we want to make a kind of a passage from ODEs to PDEs, right? So the question that we want to pose is, okay, can we prove the invariance of this Gibbs measure for partial differential equations, right? So this question sounds kind of innocent, but at least in my opinion, turns out to be somewhat deep. And in order to illustrate this a bit better, let me highlight 3 different parts of this question, right? So first, we have to ask ourselves, okay, can we even construct this Gibbs measure, right? In the ODE setting, this wasn't so much of an issue because we could just write down what it is. But in the PDE setting, we're now talking about measures of infinite dimensional function spaces, which are much more complicated. Right? Secondly, I have to worry about local robustness of my PDE, especially in our setting at a low regularity, right? In the ODE setting, again, this wasn't a concern at all because we just applied Picard-Lindelöf and it gives us local robustness. But local robustness for PDEs is much more intricate, right? And then lastly, once I've settled the existence of the measure and I have some notion of the local dynamics, I will want to prove global robustness and invariance. And the reason why I'm stating these together is because they go very much hand in hand. Okay, and this is really kind of what we want to achieve because this is how we get started on this type of problem, right? That's how we got interested in this. Now let's make this passage from ODEs to PDEs maybe a little bit more precise. So previously we had a variable q, which was real valued, and this was our unknown. Okay, we also had a p, but let's ignore that for now. And we had a potential energy. And now, for simplicity, I'll just fix this prefactor to be 1. Okay, so I have a q squared term and I have a q to the 4 term. Okay, so both of these objects will now be replaced by something that's a tiny bit more complicated. So our unknown will now be a function, which as its domain has a d-dimensional flat torus. So you can think of this as a box with periodic boundary conditions and maps into a field K, which will either be R or C. Okay. And the potential energy will again be a bit more complicated, but it will still be of this quadratic quartic type. So it consists of the integral over the square of the function, the square of the gradient, and the quartic power of the function. Right? So it's again this kind of quadratic quartic type. Now, with this potential energy, I can associate several different objects. And all of these are called 5,4D models. So these are different 5,4D models. Just in case you've never seen this notation, I always remember this by looking at this term. So here you have a phi, you have a 4 upstairs, and you have a d downstairs. Right? So this is how I remember this, this notation. Okay. Now, as we kind of saw in the ODE setting, at least at a formal level, I can associate with this potential energy a lot of different objects. Right? So first of all, I can formally write down a Gibbs measure. I can formally write down a cubic stochastic heat equation, which corresponds to the Langevin equation that we saw before. Okay. I can formally write down a cubic wave equation, which corresponds to the real valued Hamiltonian evolution equation. So exactly this kind of Hamiltonian equation that we encountered in the ODE setting. But there's one additional object which I didn't describe in the ODE setting. And this is because I'm now allowing my function to be complex valued. Okay, so to be precise, once you allow this to be complex valued, there's a different symplectic structure that you can put on your function space. And once you have a different symplectic structure, you get a different Hamiltonian evolution equation. And this different Hamiltonian evolution equation will give you the cubic Schrödinger equation, right? So this is the complex valued case. Okay. So just to highlight this again, all 4 of these different objects are linked via the potential energy. Okay, so, and I guess I didn't write down precisely what these are. I'll do that a little bit later. For now, I'm just kind of banking on the fact that these keywords, measure, heat, wave, and Schrödinger, mean something to you, right? Okay, so these type of models actually have been studied for quite a long amount of time. And we actually heard a lot about this in this seminar. So I think I will actually be citing several of our previous speakers. I do want to kind of attempt to summarize some of this literature in a table. Okay, so in the first column here, I'm listing the dimension, and this refers to the dimension of my domain, right? So remember, I had a d-dimensional torus. The second column here is about the measure. Okay, so here I'm just worried about whether or not I can actually construct this measure. The last 3 columns are about the different evolution equations, so heat, wave, and Schrödinger. And here I want to know about both probabilistic well-posedness, local and global, and invariance. Although I'll actually be a little bit imprecise whenever these 2 things were proven separately, because otherwise it won't fit in the table. So let me try to kind of start summarizing this literature. So the first type of results that were obtained were by this constructive quantum field theory community. So Nelson in '66 constructed this measure in dimension 2, and Glim and Jeffrey constructed this measure in dimension 3. Okay, and this was really one of the crowning achievements of this constructive quantum field theory school. And these are all positive results, meaning that they can actually construct this measure and prove some nice properties. Okay. The one-dimensional case is actually rather easy, but I couldn't find a reference for this from that time period. Okay, you can now find it in textbooks, but as far as I know, back then they didn't write it down. And if anybody knows of a reference, I would actually be very happy to hear about this. Okay. So, as I said, these are all positive results. A little bit later, Eisenman and independently Fröhlich proved what is called the marginal triviality of this measure in dimensions greater or equal to 5. Okay, so there are many people in this audience that know better about marginal triviality than I do. But let me just say that, roughly speaking, it means that, you know, if you can give any meaning to this measure, it will have to be Gaussian, which is often viewed as not being very sensible. So especially people in my community often regard these as kind of negative results. And as a result, this somewhat invalidates the question regarding the invariance of the Gibbs measure. And therefore, I've also colored the rest of this row in red. Okay, so I do want to say that this doesn't mean that there's kind of nothing you could study here. For instance, I think as Kubinelli mentioned in the last installment of the series, it is kind of an open problem to prove the triviality of the dynamics here. But I personally would view this as a problem that is somewhat separate from the invariance of the Gibbs measure. Now, after this, PDE people actually got interested in these type of problems. So first, the heat case in one dimension was addressed by Iwatar, then the wave case was addressed by Zitkov, and famously, Bjoern addressed the Schrödinger case. Okay. So all of these results were kind of proven in the late 80s and the early 90s. Let me stop here for a second and just say that typically these type of problems get harder from left to right. Okay, so the measure is kind of the thing that you would want to get first. And then the well-Poston's theory of heat is either then for wave, and for wave is typically easier than for Schrödinger. Okay, so there's a kind of clear error of difficulty, at least within a row. However, if you're Bjoern, you don't necessarily need to respect the order of difficulty, just go ahead and solve the most difficult problem right away. Okay. He also wrote down the wave case as a theorem in one of his lecture notes, so I'll also attribute it to him. And I would guess that he was aware of the heat case, but as far as I know, he never wrote it down. And this was actually treated independently by Daprat and Dubush, so I'll attribute it to them. Okay. So this puts us roughly at the turn of the century, and we're now about 4 decades into this research. Everything that kind of remains here is actually rather difficult, but some of it has now been addressed. Okay, so as many of you, I guess, know, there was this phenomenal work of Martin Hairer in the form of his regularity structures. And when this came out, one of the primary applications was really this parabolic 543 model, which is here. Okay. Even more recently, there was this phenomenal paper by Eisenman and Dominique, where they proved the marginal triviality for the 544 measure. And fortunately for us, Michael Eisenman actually gave a very nice talk about this in the seminar. So if you want to know more about this, you know, don't ask me, go back and watch Michael Eisenman's lecture, which was phenomenal. Okay. So as before, I will also understand this as a negative result. So I'll color the rest of this row in red. Just one comment for the experts. This case, I think, here is a bit tricky because this is complex valued and not real valued. So I'm being, I think, a little bit imprecise, but I do not want to get further into this. Okay. Good. So that leaves us with 2 different problems. And what I want to tell you about in the rest of this talk is that we've now been able to address one of them, namely in joint work with Deng, Nahmod, and Hairer-Matetski, we've now been able to prove the invariance of this measure for the 3-dimensional wave equation. The last problem that you see on this table, the one for Schrödinger, as of today, still remains open. Good. So this is about 6 decades of research, and inevitably there have been some omissions, right? I can't summarize 6 decades of research in 5 minutes. I'm not the best person to ask about partial results somewhere here. So there are, I guess, many members in this audience that know about this much better than I do. But I do want to mention at least some partial results of my own community, which lie somewhere in here. Okay, so there are a lot of results that lie somewhere in between these kind of cells. So first, there was this phenomenal paper by Gubinelli, Koch, and O, which was also briefly discussed by Gubinelli in the last talk in this series. And they addressed this quadratic nonlinear wave equation. Okay, so they didn't look at a cubic nonlinearity, they looked at the quadratic case in dimension 3. So this sits kind of in between here. Okay. There's more work by my co-authors, which treated power type NLS in dimension 2 or Hartree NLS in dimension 3. So this would sit somewhere in between here. And then there's also the bulk of my PhD thesis, which is on a Hartree nonlinear wave equation in dimension 3. So this paper got relatively close to being able to solve this. So it sits somewhere here, but it didn't quite get there all the way. Actually, the reason why I wanted to prove this result was somewhat separate. And I really wanted to prove this because it was the first case where we were able to prove the invariance of a singular Gibbs measure for any dispersive equation. So this was the first case where the Gibbs measure was singular with respect to the Gaussian free field, which is also something that will happen for us here. Okay, and there's a lot more work that one could mention here, but I tried to take kind of a wider view of the literature because I thought this was a little bit more helpful for this general audience. Okay, good. So let me kind of end this literature overview, and let's actually get to our result. So now I want to state, at least in a little bit of an informal fashion, the main result of our work. So as promised, we consider the three-dimensional cubic nonlinear wave equation. So on the left-hand side, I have my typical wave operator. So it has a second-order derivative in time and a second-order derivative in space. It also has this additional massive term, which is right here. So because of this massive term, technically speaking, I should call this a Klein-Gordon equation. But in the random PDE setting, these equations are typically not distinguished from the wave equations, because once you take into account the action of the renormalization group, it gives you the same class of equations. Okay, so this is why I still call this a wave equation. Now, on the right-hand side, we have our nonlinearity. So we have a defocusing cubic nonlinearity. So there's a minus here, which makes this defocusing, or if you prefer, repulsive. And here we have a renormalization. Okay, so these renormalizations are necessary here to counteract certain ultraviolet divergences, and that's something that is, very natural. It's considered in the physical literature, and it's considered in essentially all of the problems that I mentioned before. Right? Just as a comment for the experts, so this infinity here stands for both the Wick ordering, which is a polynomial divergence, and the additional logarithmic one that is necessary for the 543 measure. Okay. And just to highlight this again, our spatial domain is three-dimensional. Okay. Now, this is a second-order equation in time, so I'll need an initial position and an initial velocity. So this is my phi0 and phi1 here, and they will eventually be drawn from the Gibbs measure. Okay, so this is our random initial data. Okay. Now, here's our theorem. As I said, this is joint work with Deng, Andrea Nahmod, and Hairer-Matetski, and it tells you that this cubic nonlinear wave equation is probabilistically well posed with respect to the Gibbs measure, meaning that if you take your initial data from the Gibbs measure, you can actually solve this PDE globally in time. Okay, and furthermore, this Gibbs measure is invariant under the dynamics, by which I mean that at every time, our global solution has a law which coincides with the Gibbs measure. Okay, so this is really everything that we wanted to prove, and the kind of analog from the ODE setting. Okay, now let me make kind of one remark that is meant maybe for the parabolic PDE people in this audience. So if you work on singular parabolic PDE, you might be more used to seeing a stochastic forcing on the right-hand side here. Okay. In the wave setting, however, this doesn't really make a difference, at least not for the problems that we consider here. Okay, so I could add space some white noise on the right-hand side, and this could be treated similarly. And the reason is that the wave equation really doesn't smooth its initial data. So having rough initial data is roughly equivalent to having a rough forcing term. Okay. The only kind of problem where this makes a difference is if you consider questions regarding ergodicity or something like this, but that's not the topic of this talk. Okay, so just for invariance, it's pretty much the same problem. Okay, so this is our main result. Let me now kind of move on and try to give you a rather large-scale overview of our proof. Okay. So I'll split this into three separate parts that roughly correspond to the three separate parts of the question that I stated earlier. Okay, so the first thing that we'll have to talk about is this Gibbs measure. And fortunately, this was actually already the topic of many talks in this series, right? Okay, so it's not too hard to define this measure at a formal level. Okay, so there's this one kind of technicality that I'll mostly ignore. So this Gibbs measure consists of initial position and an initial velocity, right? But as we already saw in the ODE setting, the initial velocity is just Gaussian. Okay, so we'll ignore this initial velocity and focus just on the initial position. And then my Gibbs measure will correspond to the 543 measure that was mentioned before. Okay, and formally speaking, it's given by this expression right here. So I have a normalization constant, I have an exponential that contains the potential energy, and I have a bunch of Lebesgue measures, which consist of a product over all of the points in my torus. Okay. Now, as many of you know, formally this looks very nice, but if you look at it in detail, it looks completely horrible because none of this makes sense. Okay, so there is no infinite dimensional Lebesgue measure. These energies will all just be infinite, and the normalization constant will also just be infinite. Okay, so individually, you cannot really give a nice meaning to any of these, but it is possible to give a nice meaning to all of this taken together. Okay, so if you want to give a rigorous definition to this, the way to do it is to first define a finite dimensional approximation. So you can either do this by passing to a lattice instead of your continuous domain, or you can do this by truncating in frequency space. After you've truncated to a finite dimensional approximation, you will still have to renormalize. So you still have to kind of counteract the infinities, especially the ones coming from this quadratic term right here. And once you've taken care of these, or at least you believe you've taken care of them, you then have to take limits. Okay, so then you have to let your lattice spacing go to 0, or let your frequency cutoff go to infinity. Okay, and this can be done, but as you see kind of from the issue with this formal expression, it could be rather tricky. And this is why this is a major theorem. It's this theorem that was first proven by Glimm and Jeffy, and more recently has been revisited by the singular SPD community. So this has also been reproven by Brash-Gubinelli, by Gubinelli-Hoffmann-Over, and by Monod and Weber. And fortunately, these were, I think, discussed by Gubinelli in the last installment of this lecture series. Okay. So what these theorems are telling you is that this finite dimensional approximation actually converges to a well-defined limit, which is what we call the 543 measure. Okay. Some of these papers tell you a little bit more. For instance, they're interested in verifying the so-called Weightman axioms, but that's not so relevant for our talk. Okay, it's a very interesting question, but it's not very relevant for what we are looking at today. Okay. So eventually, once I have this kind of Gibbs measure, I will want to solve a wave equation. Okay, kind of in caricature form, what I will want to do is I want to start with a sample phi, and I want to solve my wave equation, and I want to find a solution phi wave, which at its initial position has a sample. Okay, so the initial position is supposed to be given by the sample of my 543 measure. Right now, there are several different properties of this measure that make actually solving this initial value problem quite challenging. Okay, so first of all, the spatial regularity of these samples is going to be just a tiny bit below 1 minus the dimension over 2. Okay, so there's a dimensional aspect to this. And in our case, the dimension is 3. Okay, so it's going to be minus 1/2. So this is a very, very low regularity that is far below 0. Okay, so making sense of any of these kind of quantities becomes extremely challenging. Now, the second problem that we kind of encounter here, or the second property of these samples that poses problems for us, is that the Fourier coefficients of our sample will be probabilistically dependent. Okay, so this statement is a bit vague, so let me clarify a bit on what I mean by this. Right? So whenever you have interactions in your theory, of course you will always get dependencies, right? That's what interactions mean. Okay, but these interactions are much more severe in the 3-dimensional setting than the lower dimensional settings. Okay, in dimension 1 and dimension 2, this 5,4D measure is absolutely continuous with respect to the Gaussian phi field, which does not have any interactions and which has independent Fourier coefficients. So in this lower dimensional settings, you can actually switch to the Gaussian phi field, and then you can have independence, right? Which is very good for you, at least if you just consider the local theory. right? But in the three-dimensional setting, it has been shown that this 543 measure is singular with respect to the Gaussian field. So this kind of trick is not available to you, and these dependencies are much more intricately linked with your problem. Okay, so these cannot be avoided. Okay. So we have these two different properties, the low spatial regularity and these probabilistic dependencies between the Fourier coefficients, right? And again, both of these has been proven, so you cannot avoid them, right? But there's still kind of one goal that we can have, and our goal can be to separate these two issues from each other, right? So we can hope to separate our samples into components which either have low regularity but good probabilistic properties. So some components which have this problem but not this one, and some other components which have bad probabilistic properties but high regularity. Okay, so they have this problem right here but not this one. Okay, so this could be still the goal that we have. We don't want to face both of these problems at the same time. Okay, and this goal can actually be achieved, and it's done using the cubic stochastic heat equation. So we actually rely on the parabolic theory in our proof. Okay, so this cubic stochastic heat equation is the one that previously featured in our literature overview, and many of you would probably call this the parabolic 543 model. So it's given by this equation right here. So on the left-hand side, I have my typical heat operator hitting my phi heat. On the right-hand side, I have my cubic linearity, a renormalization, and a stochastic white noise, right? A stochastic space-time white noise. Okay. So this type of problem remained open for a very long time, but as we discussed, can now be dealt with using either regularity structures or also the para-controlled approach by Gubinelli, Imke, Hairer-Matetski, and Kadaye and Chuk. Oh, I'm not sure how this skipped. Sorry. Yeah, so here you see that this literature overview was not a good idea from the number of slides standpoint. Yeah, sorry about that. Okay, so this has been treated now using this kind of framework. So how is this useful for us? So how do we use this heat equation? Okay, so here's our idea. So what we wanted to do was we wanted to start with a sample, and eventually we want to solve this heat equation. Eventually we want to solve the wave equation, sorry. But we'll first solve the heat equation. So we'll first solve heat, and we'll find a solution phi heat, which as the initial position has this kind of type of sample, right? And after we solve the heat equation, only then will we solve the wave equation, and we'll find a solution phi wave, which as its initial position does not have the sample that we started with, but has a solution to this heat equation at some later time. Okay, so here I'm choosing the time to be 1. To be perfectly honest, it's a little bit of a white lie and choose a small time, but I'll just ignore this here. Okay. So this may seem like cheating to some of you, because typically if I study PDEs, I'm not allowed to change my initial data, right? If my advisor told me, well, try to prove well-posedness for this PDE in L2, and I'll go back to him and tell him, oh, I proved well-posedness in H10, he might not be super happy with that, right? But in our case, this is actually allowed. Okay? And the reason why this change in initial data is allowed is because this phi heat of 1 here has the same law as the sample that we started with, because the 543 measure is invariant under the heat equation. Okay, so still essentially the same object, but just written in a different fashion. So if you may find this confusing, then there's one perspective that could help you. And the perspective that you should take here is that this cubic stochastic heat equation essentially serves as a non-trivial change of coordinates. Okay, it's still the same object we're looking at, just in a different coordinate system. So the one thing that I still owe you is why this phi heat of 1 is better than the sample that we started with. So why is this change of coordinates good for us? And the reason why it's good for us is because the phi heat of 1 has a random structure that we can leverage. Okay, so I can write this phi heat of 1 as a superposition of 3 different terms. Okay, so these 3 different terms are denoted by using different colors and different shapes. And this is a little bit unusual, but I'll be able to explain this in a couple of minutes. Okay, let me just explain for now what these are. So the first one that we encounter here, which is this blue one, this is Gaussian. So it has extremely good probabilistic properties. Okay, but it does have a very, very low regularity. It has regularity -1/2 minus. So it has this very low regularity that we were expecting to see. Okay. The third component, which we have here, which is the green component, this is the cubic Gaussian chaos. Okay, so its probabilistic properties are now a little bit more complicated than what we had before, but it now has regularity 1/2 minus. So it's already a lot smoother than what we had before, right? The last component, which is here, which is this red one, for this, we don't necessarily have much information regarding its probabilistic structure. We have some tail estimates, but that's basically everything that we have. Okay, but we don't need that because it has a very, very good regularity. It has regularity 1 minus. Okay, so roughly speaking, what happens here is a trade-off between probabilistic and analytical properties. Okay, so top to bottom, the probabilistic properties get worse, but the regularity properties get better. So there's always this trade-off. Now, let me maybe explain where these kind of colors and different shapes come from. Okay, so because of the different regularities that we mentioned here, you should view this blue data as consisting of high frequency, this green data as consisting of low frequencies, medium frequencies, sorry. So the green data consists of medium frequencies, and this red data consists of low frequencies. And then these colors just correspond to the corresponding colors in the visible spectrum of light, right? So high frequencies are typically blue, medium frequencies are green, and low frequencies are red. And this is a kind of terminology that's sometimes used in harmonic analysis that I like very much. Okay. Now, the other thing is that there are different shapes here. And the shapes actually don't have any meaning. It's just so that this is also accessible to colorblind researchers in this audience. Okay, so whenever I say blue, I mean the circle. When I say green, I mean the diamond. And when I say red, I mean the pentagon. So in our paper, we refer to these three components as the caloric initial data. And this terminology is somewhat inspired by earlier work of my advisor, Terry Tao. So in the early 2000s, Terry was very interested in wave maps, which are a geometric wave equation. And when you study geometric wave equations, you have to make a choice of gauge. And what he realized is that for the large data problem, there's a very convenient gauge, which is constructed using the harmonic map heat flow. And he called this the caloric gauge. And this has been a very popular tool in geometric wave equations. So he really had this idea to use a geometric heat equation to study a geometric wave equation. And what we're doing here is a little bit inspired by this, because we are using a probabilistic heat equation to study a probabilistic wave equation. And this is why we chose to name it after his work. Okay. So this is everything I wanted to say about the data. So let's actually move on to our wave equation, right, which is kind of the main object of interest. So we now want to talk about the local theory. So we want to examine the so-called caloric initial value problem. So the equation is still the same as the equations that we've been studying for most of this talk, just here. But the data is now given by this caloric initial data, right? And just to highlight this again, why is this initial value problem difficult? Well, it's difficult because we had a very, very low regularity. So this low regularity, deterministically, is just very, very ill-posed. And we have to somehow make up for this low regularity with probabilistic properties. Okay. So in order to use these kind of probabilistic properties, we make a para-controlled ansatz. Okay, so our solution phi wave will be written as a sum of 7 different objects. Okay, I'll explain what all of these objects are in the next couple of slides. For now, let me just mention that the first 4 are explicit stochastic objects. The 5th and 6th one are different para-controlled components. And the last one is a remainder. So here, for this remainder, we don't really use much structure. We just use that it's going to be smoother. Okay. Now, the most basic piece of information you may want to know about these properties or about these objects is their regularity, right? So the first component that we have here, which is blue lollipop, this will have regularity -1/2 minus. Okay, so the low regularity that we were expecting to see, and this is because the wave equation does not smooth its initial data. Okay. The next object that we see is this tree-looking thing, and it has regularity 0 minus. Okay, so it's a tiny bit below 0, and this will actually become important a little bit later. The next 4 components, which are these 4, they will all have regularity 1/2 minus. So they all sit a little bit below 1/2. And the last component that I have is this remainder, and this will have regularity 1/2 plus. So it will be a little bit better than 1/2. Now, one thing that you may realize is that I'm dancing around the threshold 1/2 here, right? So I have a bunch of components that are just below, and I have one component that is above. So evidently, this is an important threshold for us. And the reason why this is important is because it's the dual regularity of our lowest regularity object. So it determines whether or not I can multiply by the blue lollipop. So let's talk a little bit about what these different objects are. So the first thing I want to discuss are these explicit stochastic objects. Okay, I'll tell you their precise definition, but what I want you to remember after the slide is that they're explicit, meaning that I can write down a formula for them. I do not have to solve a fixed point problem. So the first object is this blue lollipop right here, and this denotes a linear evolution. So if I hit this with a wave operator, I just get 0. Right? Now I think it makes a lot of sense to describe a linear evolution visually by a line. Right? And I should say that this is not my idea, and so this notation has been used quite heavily by the singular SPD community. The initial data of this blue lollipop is given by the blue initial data. Right? So this is why this is denoted in this fashion. Now we have two cubic objects that occur in our ansatz. The first one is this here, and this solves an inhomogeneous wave equation. So if I hit this with a wave operator, I get the cubic nonlinearity. Okay, so there are 3 dots right here because there's also 3 dots on the right-hand side. And the initial data of this is just 0. Now I have this green lollipop, which is another cubic object. And this is defined similarly as the blue lollipop. Okay, so if I hit this with a wave operator, I just get 0. And the initial data is given by the green initial data. Right? But the reason why I call this a cubic object is because the initial data is cubic. Right? Remember, when we talked about our caloric representation, I mentioned that this green data was already a cubic Gaussian chaos. Right? So it's cubic in the heat sense, not in the wave sense. Okay. And then lastly, I guess you can see where this is going. We have this quintic object right here. And when I hit this with a wave operator, I also get a quintic term on the right-hand side. Right? So this is defined in a similar fashion. Now, there were 3 more components in my ansatz, 2 of which were pair-controlled components. Okay, so we will define x1, informally speaking, as follows. So it will be designed to absorb high, low, low frequency interactions between the blue lollipop and 2 different components in my ansatz. Okay, so these stars here, we do know what goes in there. It's just a little bit too long for the slide. The only thing that I want to highlight is that the star here involves x1 and x2. Okay, so x1 is not explicit. You have to solve a fixed point problem for it. Okay. x2 is defined similarly, but it contains high, high, low interactions between a blue lollipop, and something else. Okay. So roughly speaking, what we're trying to do here is we're trying to find all of the terms which have regularity below 1/2. And whenever we find one of them, we're trying to exhibit a useful structure. And it turns out that this paraproduct structure that we have on the right-hand side is very useful. Okay. The last thing that we'll have to do is we'll have to write down the equation for our remainder, which is this y. And when I hit this with a wave operator, I get the most complicated evolution equation of this paper. Okay, so on the right-hand side, I will see all of the different interactions, by which I mean take any 3 of the 7 different terms in your ansatz and multiply them. The only ones that we won't see are the ones that we've already taken care of, so the removed ones. So depending on how you count this, you get about 80 different terms on the right-hand side, and controlling this is really the main task of this paper. Okay, so we don't actually treat 80 cases all separately, but it's not too far away from that. Okay. So let me say a little bit about how the rest of this proof goes. So one thing that I like is that when you try to do this and you try to control all of these 80 different terms, you don't end up doing the same thing over and over again. You actually have to rely on different techniques for different terms. So we actually had to use techniques from many, many different fields. Of course, we had some PDE theory. We had a lot of probability theory. That's maybe not so surprising. But we also had some tools from geometry in the form of lattice point estimates. If you talked about Schrödinger equations, it would be more like number theory. We also did a little bit of combinatorics, which I enjoyed a lot. And we had some random matrix theory, which I guess is also probability theory, but maybe a little bit different types of probability theory. Okay. So I don't really want to go over all of these keywords, just want to get this message across that really a lot of different fields have something to say here. The one point that I do want to highlight are these type of multilinear dispersive estimates. So this really kind of controls what happens when you have kind of waves in different directions interacting. And that's something that doesn't really have a counterpart in the parabolic theory, because this is really what separates kind of our proof from the proof of the proof for the parabolic 543 model. Okay. Good. So instead of kind of going over all of these keywords, let me just tell you about two different highlights that I enjoyed very much while working on this project. So the first highlight that I want to mention here are what we call the heat wave objects. Okay, so just to recall this green caloric data, the one that we have here, this actually comes from the cubic stochastic heat equation. Okay, so it involves the heat propagator in a non-trivial fashion. Okay, and once you take products such as these, so blue times green times blue, these kind of products will contain both heat and wave propagators. Okay, and if you want to get optimal estimates on these, you really have to understand how these heat and wave propagators interact. So in order to be able to do this, we derived these kind of longhand diagrams, which are a little bit more accurate representation of what happens here. And in this longhand notation, this type of product would look like this. So I don't really want to explain in detail what all of these different objects are. I just want to highlight one aspect of them. What I want to highlight here is that there's two different types of errors. We have these dotted errors right here, and these dotted errors correspond to the heat propagator. And we have these full errors down here, and they correspond to the wave propagator. And if you want to get optimal estimates, you really have to understand what happens to a frequency like this one, if it's first propagated by the heat propagator and then propagated by the wave propagator. Okay. So this is maybe not the most difficult part of our proof, but it's something that I found very cute. Okay. Now, the second highlight that I want to mention is what we call the 1533 cancellation. In order to make a rigorous statement, let me choose n to be a frequency truncation parameter. Okay, so I'll truncate all of my frequencies to be less than capital N. The first thing I want to tell you is this 3-3 divergence. So if you look at the square of this cubic object, which I remind you had regularity 0 minus, so namely you look at this square, this actually tends to diverge as n goes to infinity in the sense of space-time distributions. Okay, so this diverges in the weakest possible topology. Okay. This divergence actually cannot be removed via renormalization. And the reason why this cannot be removed by renormalization is because the renormalization is dictated by our construction of the measure. Once we have constructed our measure, we have chosen how to renormalize, and we cannot change this anymore. Right? So this cannot be dealt with in this fashion. So this is a real problem. And when we found this, we were distraught for at least a couple of days. But it turns out that we got lucky. Right? So even though this object here diverges as n goes to infinity, if you take a linear combination with 6 times the linear object and the quintic object, and you combine all of this, this combined linear combination actually has a well-defined limit as n goes to infinity. Okay, so individually, both of them diverge, but taken together, it does have a well-defined limit. And this is what we call the 1533 cancellation. And the reason for this terminology is that there's a first-order object here, there's a fifth-order object here, and there are 2 third-order objects right here. Okay. Good. So this is everything I wanted to say about the local theory. I think that I have 60 minutes, right? So I'll be able to finish, I think, on more or less on time. And I'll, I think, use like 5 or so more. And I'll tell you maybe a little bit about the global theory. Okay, so ultimately, we want to prove global repulsiveness and invariance, right? So just to remind you what this means, invariance means that if the law of our initial data is given by this Gibbs measure, then the law of the solution at later times should still be given by this Gibbs measure, right? Now, if I want to prove invariance, I need to know global repulsiveness, right? Because if I don't know that phi of 1, let's say, exists, how am I ever going to say anything about its law? I don't even know that it exists, right? So I need global repulsiveness in order to even write down the definition of invariance, right? But how do you typically prove global repulsiveness? Right? Typically, you have some kind of conservation law, monotonicity formula, or something like this. But here, we had this very, very low regularity. And the only thing that we have that resembles a conservation law is the Gibbs measure. So we would want to use this kind of Gibbs measure as a substitute for a conservation law and use it to prove global repulsiveness, right? But now this looks very circular, and it's not so clear how you break out of this. And this is really what made Bjoern's early work so influential, because he derived an idea or a scheme of how to do this, which is now called Bjoern's globalization argument. Okay, so what you do is the following thing. You first go to a truncated system. Okay, so you truncate your PDE, and you truncate it in such a fashion that you still have a Hamiltonian evolution equation. And then you already know invariance. Okay, so once you have invariance for this truncated system, you try to combine it with some stability theory to prove global repulsiveness for this full system. Okay, and once you have the global repulsiveness, then you combine these two things and prove invariance. Okay, so this is a little bit of an oversimplification, but it still kind of conveys the main idea of Bjoern's globalization argument. Okay. And if you look at Bjoern's original setting, this is really all there is to it. But in our setting, there are actually kind of new difficulties that didn't happen before. Okay, so it turns out the singularity of the measure actually creates severe difficulties in trying to implement this. And this was already addressed kind of first by myself in this work that I mentioned on the hard nonlinear wave equation, and was also done a little bit later by Kamot and Tolomeo, so about a year later. And in our paper, we kind of further improve on the methods in there, but that would be maybe a topic for a specialized audience, and it's not so useful, I think, for this general audience. Okay. What I just want to do now is I want to leave this setting, and I want to close with something new. So I'll spend like 2 minutes to give you a little bit of an outlook. This is a little bit of a separate topic. I just want to close on something different. So this concerns geometric equations. Okay. So previously, we're interested in scalar valued equations, right? So our function phi was always real valued, or let's say complex valued. Okay. One setting that is also very natural is the setting of geometric wave equations. So what we'd like to study is a wave phi, which goes from 1 + 1 dimensional Minkowski space, let's say, into a Riemannian manifold M. Okay, so here you can think of maybe the two-dimensional sphere. Okay. Now for this type of setting, we want to write down a natural wave equation. And a good starting point for something like this is a Lagrangian. Okay, so we'll start with a Lagrangian, and this consists of a space-time integral over minus the size of the time derivative squared and plus the size of the spatial derivative squared. Right, and of course, because our function maps into the manifold, these type of derivatives are measured with respect to the Riemannian metric. Okay. Now you can write down the Euler-Lagrange equation corresponding to this Lagrangian, but because of our variable coefficient metric, the evolution equation will not be linear, and it will lead us to the wave maps equation, which is here. Okay. So on the left-hand side, we see the wave operator written in this kind of Minkowski notation. So here I'm raising indices with respect to the Minkowski metric. And on the right-hand side, we see a quadratic derivative nonlinearity with a prefactor that involves the Christoffel symbols of my Riemannian manifold. Okay. Now, for this type of equation, I also need some initial data. So I would need an initial position that maps into this manifold, and I would need an initial velocity that lies in the pullback bundle of the tangent bundle. So what this means is that phi1 of x lies in the tangent space at the position phi0 of x, right? So it has to lie in the correct tangent space. Okay. Now, the kind of deterministic theory of equations like this is by now rather well studied, but we have very, very little in terms of results that involve some kind of randomness. So a first result in this kind of direction was obtained at the end of last year in joint work with Jonas Luhrmann and Giulio Stapilani. And what we proved is essentially a probabilistic local repulsiveness result. Okay, so let's B, which is our initial position, be a Brownian path on this manifold. Okay, so it's the natural analog of a Brownian motion in the manifold valued setting. And let V be a white noise on this pullback bundle. Okay, so it's kind of a white noise derivative that is kind of always centered at the position where I currently am. Okay, and if you take this initial position and this initial velocity as your initial data, then you can actually solve this waveframes equation locally in time. So this was the result we obtained. And the main reason why I wanted to mention this result is that this is really only a starting point. Okay, so there's many, many more things that you would like to know, and there are many, many open problems in this direction that involve kind of randomness in geometric wave equations. The obvious question actually here is, can you go beyond this local repulsiveness? Can you prove global repulsiveness and invariance? And that's something that I'm actively thinking about today. But there are also other questions, for instance, related to Yang-Mills, Maxwell-Klein-Gordon, and so on. Right. So this is really, I think, a direction in which I hope to see some progress in the next couple of years. But on this, let me just end here, and thank you for your attention.
Thank you very much. Thank you very much for the very clear talk. It was very nice. Are there any questions? I have one. I mean, the first one is probably very hard. But I was wondering what you expect, or if you have any guesses about the ergodicity and mixing properties of these problems. So I guess the energy is conserved. So you can, the best you can expect is that it somehow mixes on an energy slice, and presumably that's expected to happen, I would guess. But
yeah, so I think this type of ergodicity, without any, so with stochastic forcing, there have been a few initial results now by Leonardo Tolomeo, but I guess without stochastic forcing, this has often been kind of mentioned as one of the kind of central problems in this field, but one where we don't have any idea of how to do it. You already mentioned kind of the energy here. Maybe this is not so much of an obstacle because it's just infinite, right? So you're kind of always on this infinite energy slice. But then it's not clear that there are not other things that prevent you from mixing, right? So the kind of obvious example would be something like the cubic NLS in one dimension, where you can still write down a Gibbs measure, you can prove invariance and so on. But because it's completely integrable, you can't have any mixing, right? You just have infinitely many conservation laws. And that makes kind of answering something like this very difficult. So maybe let me just say that it's a very natural and very interesting question. But I think as far as I know, almost nobody else has any idea on how to approach it.
Okay, yeah. I happened to be at a conference last week where, in fact, someone asked this question, and it's a physicist. His name is Giuseppe Musardo. He claims he has physics results on this. I took a brief look, not sure how easy it is to understand, but he claims he has a good understanding of what happens, and it sounded interesting, but I cannot say more.
No, that I've not heard about this before, so that definitely sounds interesting, and I guess it would be nice if I could turn these physics result into a math result.
It sounded pretty difficult, but anyway, his name is Giuseppe Musardo, and he said he has some on his website. And
okay, I'll take a look. This sounds cool.
Manfred.
Hello. Thanks for the great talk. I'm sort of intrigued by your 1533 cancellation.
Yeah.
Usually you'd expect, if you have such a cancellation, that there is some kind of symmetry or word identity or something behind it. Do you have any idea about that?
It's a really good question. So we've kind of looked for this, and we don't know. I mean, the kind of obvious candidate would be something like Lorentz invariance, which is strictly speaking not exactly true because we're on a torus, but approximately it is. It doesn't seem to give us this. You can play around a little bit with these type of diagrams. And so, for instance, recently I was told that something similar happens for KPZ. It's a little bit less essential there, but something similar happens for KPZ. And there were some kind of diagrammatic explanations of this. So you can kind of draw diagrams and convince yourself that maybe this happens, but I don't have a good reason that corresponds to, we have this symmetry and this is why it has to cancel. The only one, and this is a little bit like cheating, is that we believe it's not a symmetry, but we believe in the invariance of the measure, because otherwise we would have not started to prove this. And you can convince yourself that for the measure, the Wick ordered square is well defined. And then you look at the Wick ordered square initially, and you look at the Wick ordered square a little bit later, and you see that this kind of term has to be okay because the Wick ordered square has to be okay. So it's not, I guess it's a little bit like a time translation symmetry in law, but it's maybe not the most convincing either. Yeah.
Okay, thanks. So maybe can I ask a follow-up question, which is probably a sort of elementary question. I'm not familiar with your graphical notation.
Yeah.
Does this square have something to do with the two-loop diagram, which you also have to renormalize in the equilibrium?
So not necessarily. So I think the square would. So now I'm less familiar with what typically are these kind of loop diagrams of quantum field theory, but my guess would be, and maybe somebody can correct me on this, that the two loop diagrams corresponds to the additional logarithmic renormalization that is needed for the 543 measure, right? So this is something that occurs in here. So here, what you could have is a pairing between these two nodes, for instance, and this would be the two loop diagram. So this is already renormalized. The one thing that's kind of hidden in here is that there is already a renormalization of the two-loop diagram. And even after this, it still leads to this divergence. So it's somewhere, it's kind of the next order up, I guess, from the two-loop diagram.
Okay, thanks.
Yeah.
Okay, any further questions? Anyone? Well, if not, I guess we can wait another minute to see if somebody else has another one. Otherwise, thank you very much for this very nice and instructive talk. It was really nice. Thank you.
Yeah. Thank you very much for the invitation. It was a pleasure.
Thank you.